Raskas here again. So let's continue with our AP Physics 1 review 2020, talking about dynamics. This unit, which is all about forces, split into like 7 subtopics on the syllabus, and these are what they are. This normally accounts for 12 to 18%, but right now for 2020 might be up to 25% of the exam this year. So dynamics I describe as explaining motion. It's all about forces. These are some of the subtopics. We look at systems, we look at types of forces, representing forces, and then the effect of force on motion. So under systems, the main idea is you can look at multiple objects as a system as a whole. And these multiple objects moving together imply that they have the same acceleration, and within that system there are internal forces, and it's important to be able to distinguish between the internal and external forces. Types of forces, we can think of them in 2 broad categories: contact, like normal force, tension force, friction force, spring force, and then non-contact or field forces, which will be, for the AP Physics 1 syllabus, gravity and electrostatic forces. In terms of representing forces, we're talking about free body diagrams here. It's also important to choose a frame of reference and be able to resolve forces into components as needed. This includes being able to do vector addition. When we talk about the effect of force on motion, this is really where it all comes together. Everything else is more or less foundation for the effect of forces on motion. And so the big idea here is that if you have a net force, you have an acceleration. Mass opposes acceleration. And then Newton's third law, forces are interactions between 2 objects, and therefore if object A acts on object B acts with an equal and opposite force on object A. It's important to understand these equal and opposite forces are on different objects. And so when we look at the effect of force on motion, we're looking at systems, we're looking at applications of Newton's laws, and of all of these other ideas. So let's go through them real quick, and we'll sum up with 2 particularly common examples: pulleys and inclined planes. So systems, like I mentioned, they're internal forces, they're external forces. Internal forces would be examples of Newton's third law of forces. Systems move together, therefore have the same acceleration, and an important result of this is that the ratio of the net force to the mass is equivalent at all levels of the system. If you could isolate each mass in the system and the net force on each individual mass, the ratio of that net force to that mass is going to be equivalent for all the individual masses and for the system as a whole. So this is a really powerful tool to use. Now, types of forces in free body diagrams. So first of all, free body diagrams, we always draw our forces starting on the object of interest, pointing away from the object, and we only draw forces on one object in a typical free body diagram. The exception would be when we're looking at a system. We may want to draw forces on each object, and that will really be, in essence, 2 free body diagrams that we're viewing at the same time in order to help us to understand what's happening. But then at some point we're going to split it up and look at each one individually. So free body diagrams, let's focus on one object. So types of forces, these are the main ones that come up, and so you ask yourself these questions. Is it within a gravitational field? If yes, it will have a force of gravity equal to mg. Gravity always acts vertically downward. Is there a string? If yes, is that string pulling it? Is that string tight or taut? If there is, there'll be a pulling force. That's going to be Ft. And the force of tension in a string is the same magnitude throughout. So this is a really good example of Newton's third law of forces. Fn, is it touching another object or surface? If it is, there's going to be a normal force, and this will always be perpendicular to the surface and pointed away from the surface. A normal force is a pushing force. FF, force of friction, is it moving or trying to move along a surface, and is that surface rough? If it's smooth, this implies no friction. If it's rough, this implies that we have friction. If it's trying to move but not actually moving, then the force of friction will be static friction, and this can vary from 0 up to a max of mu of static friction times Fn. Kinetic friction is if the object is moving, it will only have one force of friction as long as it's moving, equal to mu k times Fn. Now, quick note on reference frames. In choosing a reference frame, we want to ask ourselves, what is the direction of acceleration or the direction of most likely acceleration? And you want to make sure that one of your components, x or y, one of your dimensions, is lined up with the acceleration. And this is very useful because it means that the other one will have no acceleration, and that allows you to sum forces in the non-accelerating dimension. You want to be able to split any force that is not in your chosen reference frame into components. And keep in mind that a component of a force is going to be a fraction of the force. The resultant or the total force must be bigger than the individual components unless one component is equal to the resultant, in which case there is 0 component in the perpendicular direction. Again, SOHCAHTOA, so when you split a force into components, look for where the angle is, and the component that is along the angle is going to be cosine of that force, and sine will be the component that's opposite of the angle. Pay attention to where the angle is drawn. So, summing it all up, this is how we apply all of these concepts. When you're given a question in which you're going to be applying any of Newton's laws, in which you're going to be applying dynamics, you want to start by drawing a free body diagram. Free body diagram should show you all of the forces on that object. If those forces are all in one dimension, then it's easy. If they are in 2 dimensions, meaning if they're not all lined up along the same straight line, then you want to choose a reference frame. Now, you want to think of what's the direction that the object is accelerating, and that will dictate how you align your reference frame. If you have forces that are not aligned with your x and y components of your reference frame, you may want to have a redrawn free body diagram in which you represent those forces by components. Now, never draw the components of a force and that force in the same free body diagram. The AP wants you to redraw it, and this is actually very useful because if you draw the force and its components in the same free body diagram, you end up looking at 3 forces instead of 1 or 2. Now, once you've redrawn your free body diagram, you want to analyze in x and y, and we're going to come back to this question of, is it accelerating? If you chose your reference frame well, then in one of those dimensions it will not be accelerating, in which case your sum of forces is 0. You can equate opposite forces. In the other dimension it should be accelerating, in which case your net force will be equal to your mass times your acceleration. So let's look at a couple typical examples. First one we look at would be an inclined plane. So an object on an inclined plane will be in a gravitational field, therefore there will be a force of gravity. That force will be acting vertically downward, not perpendicularly into the plane. That's a common mistake that some people make. Now the object will be in contact with the plane, and therefore there will be a normal force pushing out from the plane perpendicular to the plane. If that object is sliding downward or trying to slide downward and there is a rough surface, this implies that there's going to be friction. Friction will be acting upslope along the slope. However, the object may be sliding upward, and if it's a rough surface, there'll still be friction, but the friction will now be acting downslope. So friction is always going to oppose motion or attempted motion. Either way, we want to choose a reference frame that is along and perpendicular to the direction of motion and direction of acceleration. And so this object is going to be moving along this plane. So we want to choose a reference frame to suit as indicated there. Any forces that are not aligned with the reference frame need to be resolved into components in X and Y. So in this case, that would be Fg. So we'd split up Fg into Fgx and Fgy. Now we can analyze in X and Y. I'm going to do Y first because Y is going to be the direction perpendicular to my acceleration. Therefore, I know for sure that in Y there is no acceleration, which means that my net force is 0, which means that I can equate my opposite forces. So Fn is going to be equal to Fgy, which is equal to Fg cosine theta. And if you don't remember how to resolve forces on an inclined plane, you can find that on YouTube pretty easily. In the X direction, most likely my acceleration will not be 0, which means I will have a net force. Now, if I have friction, then that net force would most likely be Fgx minus friction. Now, this is an interesting case because we can go on to solve for the coefficient of friction by combining the fact that we have friction in the X analysis, but we have Fn in the Y analysis, and we can put those together because force of friction is going to be mu times Fn, and Fn is Fg cosine theta. So we get this equation, which when we solve for mu, yields this quite neat result of mu being equal to tan theta. Okay, so let's look at a second common application, pulley systems, also called Atwood's machines. So these are examples of systems of objects. We have a number of things going on here. So we have object A connected via a string that's passing over a pulley, let's call it a frictionless pulley, to object B. Object A has a force of gravity acting down on it. A string is pulling up on it, so there's a force of tension. Object B has the string pulling on it, force of tension as well. Those two tensions will be the same, assuming that this is a frictionless pulley, because tension in the same string is the same everywhere. So that's an example of third law forces. B is pulling on A is pulling on B, equal and opposite. Opposite in terms of the string. On B, there's also going to be a force of gravity, but B is resting on a horizontal surface. And if B is not accelerating into the surface or out of the surface, then there must be no net force in this direction, the Y direction on B. Therefore, there will be an Fn, and it will be cancelled out by force of gravity on B. Now notice I specified FGB and FGA. If you have more than one mass, you should specify which mass you're using for your force of gravity. It's very important. Now this seems quite complex, but what's going to happen here, let's assume there's no friction for now. This system, there's no friction, the system will accelerate in the direction as shown. Now we can simplify this system by removing the unnecessary details and redrawing it in a linear fashion, because what in essence we have is a system of two masses connected by a string in which the force of gravity on mass A is the only force that is a net unbalanced force on the system, because the forces on B are balanced, so there's no net force there. And the FTs between A and B are internal forces to the system because they're Newton's third law forces. And so what we can do then is we can group these two objects and view them as a system together. We can even represent it neatly as one object with the mass of A and B. The net force on that combined mass of A and B, or that system mass, is going to be FGA. Now, what we can do here is we can apply Newton's second law to the combined mass. The net force on on A and B is going to be FGA. The mass is going to be mass of A plus B times acceleration. We can then apply Newton's second law to each of the individual objects. On object A, we have a net force that will be FGA minus FT, and that will be equal to the mass of A multiplied by the acceleration. On object B, we have a net force that's only Ft, and that will be equal to the mass of B times the acceleration. And what brings it all together is the fact that if these objects are moving together as a system, those accelerations are the same. And so we have a system of equations. We have 3 equations here, and we can solve for anything we want given even a little bit of information. Even without information, we can get some nice expressions and things will cancel out. So that sums up the whole of Unit 2, which again is up to about 25% of the exam this year, 2020. So hopefully that was helpful. Join me in my next video where I look at examples of questions where we applied these concepts. And until next time, remember, physics is fun.